stop what you're doing, close your trading apps, put your phone in airplane mode. Because what I'm about to reveal about NVIDIA's memory crisis will fundamentally change how you think about silver investing. While everyone is focused on GPU shortages and rising computer prices, they're completely missing the hidden connection that's about to send silver to $200 per ounce. This isn't about gaming or graphics cards. This is about a supply chain breakdown that creates the biggest silver opportunity in decades. And if you don't understand this connection, you're about to miss the trade of your lifetime. Most people see NVIDIA's announcement about cutting GPU production by 40% in 2026 and think it is bad news for technology stocks. They see Micron warning that memory shortages will last beyond 2026 and worry about their laptop prices. They see data centers consuming 70% of global memory production and assume it's just an AI infrastructure story. But that is exactly what the institutional money wants you to think, while they position for what's really coming. Here's what people think is happening. NVIDIA needs more memory for AI chips, so they're competing with smartphone and laptop manufacturers for limited supply. Memory prices go up, computer prices go up, consumers buy fewer devices, and technology demand eventually normalizes when new factories come online in 2027 and 2028. Standard supply and demand cycle that resolves over time. The contradiction lies in the mathematics of the shortage itself. When NVIDIA's CEO Jensen Huang says his company's demand alone requires every memory factory to gear up, and when Micron's executive says they can only meet 2/3 of medium-term requirements even for existing customers, we're not talking about a temporary imbalance. We're talking about permanent structural demand that exceeds manufacturing capacity by orders of magnitude. This is where the narrative breaks completely. Because the hidden mechanism driving this crisis isn't just about memory allocation, it's about the physical materials required to manufacture the alternatives, the substitutes, and the infrastructure needed to work around memory constraints. And the most critical of those materials is silver. Let me explain exactly how this works. When memory becomes too expensive or unavailable, electronics manufacturers don't just raise prices and wait. They redesign systems. They optimize architectures. They find alternative pathways for data processing and storage. And every single one of these alternatives requires more silver per device than the original memory-intensive designs. Consider what happens when a smartphone manufacturer faces memory costs that represent 25% of their bill of materials instead of 15%. They can't just pass that cost to consumers because demand becomes price inelastic. Instead, they redesign the device architecture to use less memory while maintaining performance. This requires more sophisticated circuitry, more advanced power management, and more efficient signal processing, all of which demand dramatically higher silver content. The same principle applies across every category of electronics affected by the memory shortage. Laptops, gaming consoles, data center servers, automotive systems, industrial equipment. When memory becomes a constraint, engineers solve the problem through silver-intensive alternatives. But here's the part nobody is calculating. The scale of this redesign effort is unprecedented. We're not talking about optimizing a few product lines. We're talking about reimagining the fundamental architecture of every electronic device manufactured globally because memory has become permanently scarce and expensive. NVIDIA's memory crisis is forcing the entire electronics industry to pivot towards silver-intensive solutions simultaneously. And the silver market has no capacity to absorb this demand shock. The escalation becomes clear when you understand the timeline compression. Memory shortages aren't resolving in 2026. Micron explicitly states the crisis continues beyond 2026. SK Hynix has sold out their entire 2026 production capacity. Samsung is prioritizing AI customers over traditional electronics manufacturers. This means the redesign towards silver-intensive alternatives isn't a temporary adjustment. It's a permanent restructuring of how electronics are built. The institutional money recognizes this shift is already underway. While retail investors focus on NVIDIA's stock price and worry about GPU availability, sophisticated players are accumulating physical silver and silver-related assets because they understand the materials science behind the electronics redesign. Data centers provide the clearest example of how this unfolds. When memory costs become prohibitive, data center operators optimize through different approaches. They use more sophisticated networking equipment to reduce memory requirements per server. They implement advanced cooling systems that require more electrical conductivity. They deploy power management solutions that depend heavily on silver's unique properties. Every optimization that reduces memory dependency increases silver dependency, and data centers are consuming 70% of global memory production, which means their optimization efforts alone represent massive silver demand acceleration. Now the mid-story reversal. The real winner isn't NVIDIA, isn't memory manufacturers, isn't even electronics companies that successfully navigate the shortage. The real winner is whoever controls silver supply when the electronics industry realizes that memory constraints force permanent silver intensity increases across every device category. But there's something the market hasn't priced in yet. The memory shortage isn't just affecting new product development, it's forcing retrofits and upgrades of existing systems. When data centers can't get enough memory to upgrade servers, they compensate through networking and infrastructure improvements. When automotive manufacturers can't get memory chips for new vehicles, they enhance electrical systems and connectivity through silver-intensive components. This creates retrofit demand on top of new product demand. And retrofit demand is typically more price inelastic because it's driven by operational necessity rather than consumer preference. The scope of this retrofit market becomes staggering when you consider the installed base. Billions of devices, millions of vehicles, thousands of data centers, all potentially requiring silver-intensive upgrades because memory solutions are unavailable or economically prohibitive. Meanwhile, silver mining production remains constrained by the same factors affecting memory manufacturing: long development timelines, environmental restrictions, capital intensity, and regulatory complexity. The difference is that silver mining faces additional challenges from energy costs and geopolitical risks that memory manufacturing does not experience. Here's where the systemic consequence becomes unavoidable. When electronics manufacturers globally pivot towards silver-intensive designs due to memory constraints, and when retrofit demand accelerates from existing systems unable to access affordable memory upgrades, and when silver mining cannot respond quickly to demand increases, the price adjustment mechanism has to eliminate marginal demand. But unlike memory, where marginal demand can be eliminated through design optimization or delayed purchases, silver demand from electronics redesign is largely inelastic. The silver is required for the alternative solutions to work. There are no substitutes for silver's electrical and thermal conductivity properties in high-performance applications. This creates what economists call a supply-demand scissor. Demand becomes more inelastic as electronics redesign accelerates, while supply remains constrained by mining and refining capacity limitations. The only adjustment mechanism is price appreciation until enough marginal applications get priced out of the market. Bank of America's recent analysis suggesting silver could reach $309 per ounce suddenly looks conservative when you factor in the electronics industry's forced pivot away from memory, intensive designs towards silver-intensive alternatives. The timeline matters because the memory crisis is accelerating rather than resolving. NVIDIA cutting GPU production by 40% in early 2026 isn't the end of demand destruction. It's the beginning of design pivot acceleration. Every manufacturer facing memory shortages or prohibitive memory costs starts redesigning immediately because waiting makes the problem worse. The Federal Reserve's recent monetary policy decisions add another dimension to this analysis. When electronics costs rise due to memory shortages, and when manufacturers pivot to silver-intensive alternatives that further increase production costs, the resulting inflation isn't temporary or cyclical. It's structural and persistent. Traditional monetary policy tools become ineffective because the inflation stems from resource constraints rather than excess demand. Raising interest rates doesn't increase memory production capacity. Reducing money supply doesn't accelerate silver mining. The Fed faces the same policy constraints that Bank of America identified in their precious metals analysis. But the international implications extend beyond just U.S. monetary policy. China dominates electronics manufacturing, but doesn't control memory production, which is concentrated in South Korea and the United States. This creates strategic vulnerabilities that force Chinese manufacturers to pivot towards silver-intensive alternatives more aggressively than Western competitors. When Chinese electronics manufacturers face memory supply disruptions due to geopolitical tensions or supply chain weaponization, they can't just wait for normalization. They must redesign products using available materials. And the most effective available material for high-performance electronics is silver. China's electronics industry represents approximately 30% of global production. If Chinese manufacturers accelerate their pivot to silver-intensive designs due to memory supply security concerns, it adds geopolitical demand pressure on top of the technical demand pressure from memory constraints. The mining response to higher silver prices faces additional complications that don't affect memory manufacturing. Environmental regulations for mining operations have become more stringent globally. Community opposition to new mining projects has intensified. Permitting processes take years even for expansion of existing operations. Most importantly, silver mining economics require sustained high prices to justify new development because of the long payback periods and high capital intensity. Short-term price spikes don't incentivize major capacity additions if miners doubt price sustainability, but the demand from electronics redesign isn't speculative or cyclical. It's structural and permanent. Once manufacturers redesign products to use silver-intensive alternatives because memory is scarce or expensive, they don't redesign back when memory becomes available again. The silver-intensive designs often perform better and become the new standard. This creates the demand permanence that silver miners need to justify major expansion investments. But the expansion timeline still requires 5 to 9 or 7 years for meaningful capacity increases, while the electronics redesign timeline operates in months. The investment implications extend far beyond just buying silver or silver mining stocks. The electronics industry's pivot towards silver-intensive designs creates winners and losers across multiple sectors that most investors haven't identified yet. Electronics manufacturers with superior silver supply chain relationships gain competitive advantages. Companies with silver-efficient design capabilities can maintain margins, while competitors struggle with rising materials costs. Businesses that provide silver recycling and recovery services become strategically valuable as silver intensity increases across electronics. But the most significant implication is for traditional portfolio allocation models. When a structural shift forces an entire industry toward dependence on a scarce physical commodity, the commodity becomes a necessary rather than speculative investment. Silver allocation shifts from optional diversification to mandatory portfolio component. Let me walk you through the specific mechanics of how this electronics redesign accelerates silver demand beyond anything the market has priced in. When smartphone manufacturers face memory costs representing 25% of their bill of materials, they implement several silver-intensive workarounds. Advanced power management systems that reduce memory access requirements use silver-based conductors for efficiency. Enhanced signal processing chips that minimize memory bandwidth needs require silver interconnects for high-frequency performance. Improved thermal management systems that prevent memory overheating depend on silver's superior thermal conductivity. Each optimization strategy increases silver content per device while reducing memory requirements. Multiply this across billions of smartphones manufactured annually, and the silver demand increase becomes massive. Data center optimization follows similar patterns, but at much larger scale. When memory costs force servers to operate with constrained RAM, data center operators compensate through networking infrastructure improvements. High bandwidth interconnects that reduce memory bottlenecks require silver-plated contacts and conductors. Advanced cooling systems that maintain performance without memory upgrades use silver-enhanced heat exchangers and thermal interfaces. The scale difference is crucial. A smartphone optimization might increase silver content by 0.1 ounces per device. A data center optimization might increase silver requirements by hundreds of ounces per rack. With data centers consuming 70% of global memory production, their optimization efforts represent exponentially larger silver demand than consumer electronics. Automotive systems face the most extreme redesign pressures because vehicle electronics cannot be easily upgraded after manufacture. When automotive manufacturers cannot source sufficient memory chips for advanced driver assistance systems, they must implement alternative architectures that provide equivalent functionality through different approaches. These alternatives typically involve distributed processing networks that require more interconnects, more sensors, and more communication pathways. Every additional connection point, sensor interface, and signal pathway increases silver requirements. The automotive industry's pivot toward electric vehicles simultaneously increases silver demand from battery systems and electronic systems. The compounding effect occurs when memory shortages force automotive manufacturers to delay advanced features while maintaining basic functionality through silver-intensive alternatives. Instead of one advanced memory-based system, vehicles implement multiple distributed silver-based systems that collectively use more silver than the original design would have required. Industrial equipment represents another massive demand source that hasn't been quantified by silver analysts. Manufacturing automation, process control systems, and monitoring equipment all face the same memory constraint pressures as consumer electronics. But industrial equipment operates in environments that require higher reliability and longer service life, making silver's corrosion resistance and electrical stability even more valuable. When industrial equipment manufacturers cannot access affordable memory for system upgrades, they extend equipment life through silver-intensive maintenance and enhancement programs. Electrical contact replacement with silver-enhanced components, conductor upgrades for improved signal integrity, and thermal management improvements for extended operation under memory-constrained conditions. The industrial retrofit market operates on much longer cycles than consumer electronics, but with much higher silver intensity per application. A single industrial facility retrofit might require hundreds of ounces of silver compared to fractions of an ounce for consumer device optimizations. The currency implications mirror Bank of America's analysis, but with additional urgency. When electronics costs rise due to memory shortages and silver intensity increases, the resulting inflation pressures create monetary policy constraints that force currency devaluation as the path of least resistance. Central banks facing structural inflation from resource constraints rather than demand excess have limited policy options. They can't create more memory or silver through monetary expansion. They can only accommodate the price increases through currency adjustment. This accommodation validates precious metals as superior stores of value compared to currencies experiencing structural devaluation pressure. Silver benefits from both industrial demand increases and monetary devaluation simultaneously. The Federal Reserve faces particular constraints because electronics price increases affect core inflation measures. Unlike food and energy price volatility, electronics inflation from resource constraints doesn't reverse quickly. Memory shortages and silver intensity increases create persistent upward pressure that requires sustained monetary accommodation. But monetary accommodation to offset electronics inflation risks creating broader price instability across other sectors. The Fed cannot target electronics affordability without affecting overall price levels. This policy dilemma forces acceptance of higher structural inflation or economic contraction from electronics industry disruption. International trade implications add another dimension to the analysis. Memory production is concentrated in South Korea and Taiwan, creating supply vulnerabilities for electronics. Manufacturers in other regions. When geopolitical tensions or supply chain disruptions affect memory availability, manufacturers cannot simply wait for normalization. They must redesign products using locally available materials and suppliers. Silver mining and refining operations exist in more geographically diverse locations than memory manufacturing, making silver-intensive designs more supply chain resilient than memory-intensive alternatives. This supply chain security consideration accelerates the electronics industry's pivot towards silver-intensive designs beyond what pure economic factors would suggest. Manufacturers value supply chain resilience as much as cost optimization, especially for critical applications and strategic products. China's electronics manufacturing dominance creates particular silver demand pressures. Chinese manufacturers face both economic incentives and strategic necessities to reduce dependence on foreign memory supplies. Silver-intensive design alternatives provide technological sovereignty that memory-dependent designs cannot offer. The scale of China's electronics production means their strategic pivot towards silver-intensive alternatives represents massive demand increases concentrated in short time frames. Unlike gradual market evolution, strategic realignments happen rapidly and decisively. The mining industry's response capacity becomes the critical constraint determining how extreme silver price appreciation becomes. Current global silver mining production totals approximately 800 million ounces annually. Industrial demand already consumes roughly 500 million ounces, leaving 300 million ounces for investment and monetary applications. If electronics redesign efforts increase industrial silver demand by just 50%, it would require an additional 250 million ounces annually. That represents more than 80% of current non-industrial supply. If electronics demand increases by 100%, which seems likely given the scale of memory constraints and redesign efforts, industrial demand alone would exceed total global mining production. This arithmetic makes clear that significant silver price appreciation is not optional. It's mathematically required to balance supply and demand. The question becomes how high prices must rise to either incentivize new mining production or eliminate enough marginal demand to restore equilibrium. Historical precedents suggest that supply-demand imbalances of this magnitude require price increases of 200 to 400% to restore balance. Starting from current silver prices around $90, that implies price targets between $270 and $450 per ounce. Bank of America's $309 target falls within this historically derived range. But historical precedents might underestimate the severity of current imbalances because they don't account for the simultaneous occurrence of memory constraints, silver demand increases, mining capacity limitations, and monetary policy accommodation. The convergence of these factors creates conditions more extreme than individual historical episodes. The timeline compression creates the most dangerous scenario for unprepared investors. The electronics industry's pivot to silver-intensive designs isn't waiting for memory shortages to resolve. It's accelerating because manufacturers recognize that memory constraints are permanent rather than temporary. Every month of delay in positioning for this structural shift makes the eventual adjustment more expensive. Silver purchased at current levels provides exposure to industrial demand increases that haven't been priced into the market yet. Silver purchased after the electronics redesign becomes obvious to mainstream investors costs significantly more. The wealth preservation implications extend beyond just investment returns. When structural shifts force entire industries to depend on scarce physical resources, ownership of those resources becomes essential for maintaining purchasing power. Silver ownership shifts from speculative positioning to defensive necessity. But here's the cliffhanger ending that should concern every investor, regardless of current silver exposure. The memory crisis analysis assumes that electronics manufacturers can source sufficient silver to implement their alternative designs. It assumes silver markets can absorb the demand increases from industry-wide redesign efforts. It assumes mining operations can scale production to meet both traditional demand and electronics pivot demand. What if those assumptions prove optimistic? What if the electronics industry's pivot towards silver-intensive alternatives creates physical shortages that make current memory constraints look manageable? What if silver becomes the next critical material that limits technology innovation and economic growth? The structural problems driving NVIDIA's memory crisis aren't resolving. They're intensifying and spreading to other materials. The electronics industry's response creates new resource constraints that could prove even more disruptive than the original memory shortages. When an entire industry is forced to redesign around a scarce physical material, the price discovery process doesn't follow traditional supply-demand curves. It follows panic buying, strategic hoarding, and allocation rationing until equilibrium is restored at dramatically higher price levels. The hidden connection between NVIDIA's memory crisis and silver prices isn't just about electronics redesign. It's about the cascading resource constraints that occur when industrial-scale substitution efforts exceed the capacity of alternative supply chains. The question is not whether silver reaches $200. The question is whether $200 is enough to restore supply-demand balance when the entire electronics industry pivots toward silver intensity simultaneously. The answer depends on how quickly you recognize the connection and position accordingly.